Okay, so today we will be covering some of the questions in the homework. Your TA is not here, I'm doing it instead of him today. Let me just turn this thing off. So the first question that I will be covering would be question number 2. Everything is from the homework number chapter 6. So first question is question number 2. Yes, Bryn, it's me. Come. Today it's me instead of your regular TA. He has an exam. Okay. Yes, I'm starting right now. So the first question that we're covering is about uh, exercise number 2, which talks about suppose that one-celled organism can be in one of the two states, either state A or state B. An individual in state A will change to state B at an exponential rate alpha. An individual in state B divides into two new individuals of type A at an exponential rate beta. Yes, that's me. I see so many new faces. Define an appropriate continuous time Markov chain for a population of such organisms and determine the appropriate parameters for this model. So this is the first homework. So I guess all of you have the solutions already or no? Okay, so it's good to have them on your hand because then I can refer to them easily. So the first question talks about these two organisms, and we want to find the continuous time Markov chain which models it. So there were two times to model continuous time Markov chains. There was one that you specified the transition matrix for the embedded Markov chain, the discrete time, and then the rates. And the other one was just to give the transition rates. So let's do it first for the. So in the back of the book, one method is explained. So if you have your book with yourself, you can look at it on page 726. So if we are in a state, so our state, first we have to define our state space correctly. So our state space would have two components. One of them would be n, and the other one would be m, the components of our space. N would be the number of people in number of the population A, and this would be the number of the people who are in population B, from the population B, sorry, organisms. Now the transition rate for each of the guys from population A changes to somebody in population B at rate alpha. So we are leaving this, and they are individual. They are all independent, and they behave with the same way. So the rate that we are leaving this state would be alpha times multiplied by the number of individuals. Wow, everybody's late. So alpha n plus, then we have the second rate would be just the departure from this state through these guys, the m guys, which would be beta is the rate that these change to the organisms multiplied by the number of the people in that population. So this would be the rate that we are leaving this state. And the other thing that we need is the probabilities that when we are leaving this state, where we are going. And then we have characterized our Markov chain completely. So those probabilities would be, first of all, let's first find which states we can go from. So when we are in the state n and m, two things can happen. Either this can, one of the a's changes to one of the b's, if I'm sure. Yeah. So what we would have from this state, we can either go to a state n minus 1 and m plus 1, which means one of the organisms in population A has changed to one of the organisms in population B, or we have the other way back. But for this one, we know that this will go to n plus 2 and m minus 1, if I'm correct. So the reason was that one organism in B changed to two of its two A's. So that was how the evolution of the system. And we just need to find the probabilities of this thing happening. But we know the individual rates, how they behave. So the probability that we go from a nm to state n minus 1 and m plus 1 would be just the rate that we are leaving this state to this state divided by a whole rate. So it would be alpha n divided by alpha n plus beta n. And the probability that we will be going from state nm to n plus 2, m minus 1 would be just beta m divided by alpha m plus beta m. So basically, this is how you characterize the Markov chain, the continuous time Markov chain that we have here. So there were two ways to characterize the Markov chain. One of them was this. So we give the transition rate, and we also give the probabilities. So this was one way to characterize Markov chains. The other one was just to give the transition rates for each state. So you would say that you go from this state to some other state with these rates, and you specify it for all possible states, and then you're done. So if you remember, we called that notation Q of ij, which is the rate that we are leaving state I going to state j. And remember, I is something like n and m. So each of these has two components in the states. So it would be just the rate that we are leaving a state I, which is this guy, multiplied by probability that we are going from state I to state j. And that's how you define the transition rate. So you either give this matrix, which would be Qij, Q, so Qij, if this is I, this is j, equals I, Qij. So you either specify the whole continuous time Markov chain by giving this matrix, or you just specify what the transition rate is in total from one state, and you tell the probability that you leave one state and go to some other state. So is this clear? I think for this one you had even the solution in the back, so I'm not sure if it really needs that much explanation. Now, the next question that we have is question number 3. Okay, this is a nice question. So, let's see. Yeah. Question? Oh, okay. I can use the other part. That's fine. Okay. So the second question, the third question talks about birthday. Well, it doesn't say that. So let's first read the question. It says, consider two machines that are maintained by a single repairman. Machine I functions for an exponential time with rate mu I before breaking down. Either I is 1 and 2, and the repair time for either machine are exponential with rate mu. Can we analyze this as a birthday process? If so, what are the parameters? If not, how can we analyze it? Okay, so what was the birthday process? Any idea? Remember? So a birthday process was something that, can I read it now? This part? So a birthday process was something that when we draw it, states you could either go from this state to this state, or you could go either to your neighbor. So basically you couldn't jump. That was the idea that we had for birthday processes. Obviously not all Markov chains are birthday processes, because there is a Markov chain you can just show this. Okay, so it's a special case of a Markov chain in this example. Now the question is asking us if we can analyze it as a birthday process. Let's first, yes.
What number is this from?
Question number 3. 3, yeah. It's the second question that I'm do you have your homework solutions with yourself? If you have them, I'm also going over. Oh yeah, if you have the book, that also helps. It's on page 391. Now the question is asking us if we can analyze it as a birthday process or not. Let's first forget that part and just see if we can analyze it as a continuous time Markov chain, find out the probabilities, and then we will see if it's possible to analyze it as a birthday process too or not. Which, by the way I'm talking about it, you should guess that it's not. Now, let's see what we have here. I should get. Okay, so let's think of our states. So we have two machines machine 1 and machine 2, and each of them can either be working or not working. So the states that I will have, this is well, after working a while with them, you will see some natural states that come into your mind. So to make it an easy one-dimensional state, it would be, let's say, we call the states, let me just use the same names that we have here. B1, 2, 0, 1, and 0, 2. So B is the state when both are working. Both are working. 1 is the state that 1 is working, but 2 is being repaired. 2 repaired. Now 2 is the other way around. 2 is working, 1 is being repaired. 0, 1 means that none is working, but 1 is being repaired. And 0, 2 means, again, none is working, but 2 is being repaired. So this would be a natural way to illustrate this as a continuous time Markov chain. The next step would be to represent our Markov chain. Again, there are two ways, either to use the rates or to use the rates Qij, or just find the total rate that we are leaving this state and give the probability distribution. So you will see that sometimes one of them is easier the other way. This time, this one is much easier to use. And we just write it down easily. Now, just to make sure that I'm not making a mistake. So, the first thing is that some of these transitions obviously cannot happen. There is no transition from B to this one, because not both of them can break down at the same time. Markov property, not two things happening at the same time, all these things. So the first thing that we have is when both are working, and we go to the state that 1 is working, 2 is being repaired. So we go here with the rate of second one's failure. So it would be mu2. That's what it's called in the question. So is it clear why I wrote this one? Because if you get this one, then the rest would be just okay. Now, the second one would be mu1. So this is the rate that we will be going from both working to the case that only 2 is working, which is equal to the failure rate of the first one. Now, we cannot go from B to any other place. Now, from 1, when 1 is working and 2 is being repaired, we can go back to B. This means that 1 is still working, but 2 is now repaired. So what was the rate of the repairing? It was called mu. So we go back with rate mu. Now, the second rate would be from Q1 we can go to Q. Okay. Now we cannot go from Q1 to Q01. It means that when 2 was being repaired, if 1 breaks down, we go to the state that none is working but 2 is being repaired. Okay? So we can go from Q1 to 02. It means that the state that only 1 was working and 2 was being repaired, we go to the case that none of them is working, but 2. So this would be equal to just the rate of failure of 1, which would be mu1, if I'm not mistaken. Okay, now I think did I make a mistake? Q0, Q1 to 0. No, that's right. No. The next step would be, now, we have the same thing exactly for 2. So from 2 you can go to B, which would be with the rate mu. It means that 1 is repaired and we go back to both working. From 2 we can go to 0, 1. This would be with rate mu2. So we took care of the cases this, and now we go here. Now, from the state that none of them is working and 1 is being repaired, we can go to one state only. And that's the state that 1 is now working and 2 is being, We go to the state that 1 is working, 2 is being repaired. We go here by rate mu. For the case that 2 is being repaired, we can only go to the case that 2 is repaired and 1 is being repaired, which is mu. I think this should exhaust all cases. 8. Yes, I have all 8. So that's it. Now, so and there's also, we have to make sure that that's it. Yeah. So remember, how do you define the rates? For example, QBB minus some of the rates on that row. Nothing really fancy. So you normally even don't need to specify it because it's just trivially known. So forget this part. So this would be the transition rates that we will have. Alternatively, you can again come up with the other way to characterize it, which was writing the it was easy to do it this way because we already had the rates. But now let's try to characterize it the other way. We have the probability. We want to define the probability matrix for the discrete Markov chain which is happening there without any rate and just giving a exit rate. Now, so what would be the rate, for example, that we are leaving state B? The rate that we are leaving state B would be the sum of these two rates. Because from B you would either go to 1 or 2. So it would be mu1 plus mu2. And then you also have to give the probability that you go from state B to 1 or you go from state B to 2, which would be probability of going, for example, from B to 1 is the rate that you go from B to 1 divided by the total rate that you escape. So you could either characterize the whole continuous time Markov chain with this set, or you have to write this type of things. Of course, there is a second one which PB2 would equal to mu1 plus mu2. So this is for the state B. So for each of the states, each of these 5 states, you can give these 3 equations and characterize the whole Markov chain, or you can just do it by this. Both have about the same thing. You can derive each of them from the other one. Now, the question talks about if you can model this thing as a continuous time Markov chain. A birth-death process. Now, to model it as a birth-death process, we can just look at the states. What do they have? Okay, just look at the states that we have. We have B, 1, 2, 01, 02. Okay. So from B, we can either go to 1 or 2. So to make it look like a birth-death process, let's put B here, 1 here to here. So you can either go here or you can either go here. From 1, you can either go back to B, which is fine, or from 1 you can go to 02. So let me put this thing there. Yeah. From 2 you can either come back to B, or from 2 you can go to 01. Up to here it's totally fine. Now, from 01, it means that 1 is being repaired. You can go back to here. And that's the only place that you can go. And from 02, you can go back to here. Well, this is one way of putting the states. And in this way, we can see that it's not a birth-death process, because it's not the case that anybody can go only to his neighbor and nobody else. That was the meaning of a birth-death process. You can try all different combinations with more than one-dimensional states. It will be the same thing. So there's no way to characterize this continuous time Markov chain as a birth-death process. So you cannot use, if it was a birth, well, we have examples of birth-death process, so we'll talk about it later. But when it's birth-death, you have a lot of nice theories that you can apply. But in this case, we don't have them, so we just have to stick with what we have. Questions? No? Good. Now, next one is question number 4. Okay, and the answer for it is also on the back of the book, page 727. Now, so it talks about This one talks about, is this the barber question? No, it's just a customer and server, no barber here. So potential customers arrive at a single server station in accordance with a Poisson rate lambda. So let's say we have a server that people come with rate lambda. And if the arrival finds n customers already in the station, he will enter the system with probability alpha n. So we'll assume that there are n guys here. We'll enter with probability alpha n. And assuming that the exponential rate mu, so this side goes out, this rate mu, set this up as a Berthet rate. This should be very easy. So if there's a step that you think is ambiguous, just let me know. So obviously the states would be what? Number of customers. Now, we have no other number even in the question to guess, so that's the only thing that we can go. So 1, 2, 3, up to anything. Well, there is no, yeah, this can go up to infinity. There is no, so when we are at 0, we go to 1 with rate alpha 0. So if somebody comes, lambda alpha 0. So if somebody comes, they come with rate lambda, and they see nobody here, so they enter with probability alpha 0, or with probability alpha 0 they don't enter, 1 minus alpha 0. When you are at state 1, you come back to in this state it's mu, because it's just a service rate independent of the number. For the next step it would be lambda, but now this guy can come, sees one person, so it would be lambda alpha 1, and we come back here with rate mu, and so on. So when we are at state n, we either go to n plus 1 with rate lambda alpha n, or we either go to n minus 1 with rate mu when n is greater than or equal to 1. And when you're in 0, you can obviously just go up. You cannot go negative. It's clear? Yeah.
Until you reach the n, you always enter the system just with alpha. And when
Does it say it like that? In the station, it will enter with the system with probability alpha n. So the first person who comes, well, forget the first person.
And it's like 6 or something. I mean, you can understand that the customers enter with alpha until 6, then they begin with, then either, leave the system or go somewhere else.
Okay. So let me see if I got your question correct. So basically you are saying that if, for example, n equals 6, then until the state 6, people enter with probability alpha, and then after that they enter with probability...
Then it changes.
No, that's not what the question means. You cannot interpret it that way. So basically the interpretation is there's only one way to interpret it. Think of it like this, that so you come and you see a certain number of people there, and there's a probability distribution that you enter or you don't enter. And this probability distribution only depends on the number of people that you see. So for example, when the first person comes, there is nobody there. In that case, we say it's, let's say, half and half. So with probability half, he enters, with probability half, he doesn't enter. So if the rate is lambda, with probability lambda, with rate lambda over 2, they enter. Assume that in case 1, it changed, this probability distribution changed to alpha 1 equals to 1 over 3, thus minus alpha 1 equals to over 3. So it means that if somebody comes and sees only one person in the system, there's a 1/3 probability that he enters, there's a 2/3 probability. So it would be, it doesn't need to be increasing or decreasing. It can be anything. It can be, in fact, alpha n. That's how he makes it abstract. So it just means that you have to just, what the key idea, the key concept is here, that you can say that when people come with rate lambda, there are two types of customers. Those with rate lambda alpha n, and those with rate lambda 1 minus alpha n. These are those who enter, these are those who do not enter. That's all the thinning process that's happening there.
question. If we, for example, there are 12 people in the system,
Okay, good.
then you know
There's the 13th person who
our
comes,
rival fence
12.
12. I mean, it had 6 already there, plus another 6, but you know.
I think I'm not getting your question.
No, okay.
We can talk about it then. But I think it should be pretty clear. It's nothing that fancy. Maybe you're just thinking something hard because it's a very easy question. Don't think anything, fancy is happening here. It's just a normal question. Now, question number 7. Okay, this is a nice question. Let's think of it. So, individuals join a club in accordance with a Poisson process with rate lambda. Each new member must pass through k consecutive stages to become a full member of the club. Think of it as exams, tests, whatever. Then the time it takes to pass through each stage is exponentially distributed with rate mu. Let NIT denote the number of club members at time t who have passed through exactly right stages. Okay, let's draw the picture. Normally in these things, when you draw the picture, it's really easy to get the question. Yeah, okay. I just erase it up to here. So question number 7. So we have this club which has some stages, exams, whatever, and then here you become a member. Okay. So let's see how many stages there are. There are k stages. So stage 1, 2, up to k. And people enter with rate lambda. And then at each stage, it takes the time to pass. Okay, this is the rate mu here. This is the rate mu here, which is independent of the stage. So each stage has the same distribution, the time that it takes. And then NIT, so for example, N1T equals number of people in the stage 1 at time t. So N1T refers to this. The same thing, we have N2T to NKT. And, k minus 1. When you go to stage k, you are a member. Okay, so that's the last stage. Now, the first question is this a continuous Markov chain? You should check if it is, if there is a, yes or no? Yes, okay, yes. So it's trivially a continuous time Markov chain because think of it like this. So we have N1T to Nk minus 1T. So at each time there is only one thing that can happen. You cannot have two transitions at the same time. So so this would go to, just think of it as a generic case. You go from Ni, let me just write down correctly so that I don't make a mistake for that. Let me just write down the states correctly. So you have N1 till Ni plus 1, Nk minus 1. So these are number of people in each stage. So this thing can go to N1, Ni minus 1, Ni plus 1 plus 1, Nk minus 1. So that's how transitions happen. You can go, there's only jumps up. There is nothing jumping down. So you can go from this stage to this stage. You can go backward. And you go from each stage to the other stage with exponential. This is just definition of a Markov chain. Nothing more than that. It's just a Markov chain if you think of it as a birthed process. We have not talked about if it's a birthed process yet, but if you just think of it like that, it's something like which you only have jumps like that. Do you remember what was it called? The birthed process, which was only birth, no death? Only birth, no death. Do you remember elves in the Lord of the Rings? They didn't die. It's like that. So it would be a Yule process. We'll have an example of that. So it's just something which always goes up. Of course, at the end, we will see this one can go down. This is the only one that we'll talk about it. Now, so the first step is that, yes, it's a Markov chain. Then the question asks, let me find my questions. Then the question asks, if so, give the transition rates. So the next step is to find the transition rates. Now, for that, we have to be a little bit more careful about our transition states, that's how they change. So this is one kind of transition that we can have, going from such stage to such stage. But there are two special stages, the first one and the last one. So we just have to make sure that how these two change too. Normally it's the case for all the Markov chains, the last one, the first one, they're a little bit different. So from this stage, we can either go to 1, which is this, or we can either go to something like this, n1 plus 1, n2, nk minus 1. So in this first one, somebody in the stage I went to stage I plus 1. In this second one, somebody just entered a new applicant. And in the last one that we can have is n2, nk minus 1 minus 1. It means that a last person graduated or became a member. You can think of it. So we can have these three types of transition from a state like this. Of course, all of these are contingent that these are not 0. So, for example, this one is not 0. For example, if we have nobody in this stage, so this is 0, we can obviously not go to this stage. That's not a very important thing. Now, we just have to find what's the rate. So any guess for the rates? Should be pretty easy. So what's the rate that we go from here to here? Mu. So mu is the rate that one person goes from here to here. Then how many are there? Ni. So the rate would be, just make sure, what's the notation here? It's just the same thing. So going from stage, let's call this star. So going from stage star to stage 1, which would be with rate Ni mu. And going from stage star to stage 1, what is the rate for that one? Going from a stage star to stage 2. So from a stage star to stage 1, it was that somebody in I goes to I plus 1. So somebody graduates from here, goes there with rate Ni mu, because there were Ni, each of them at rate mu. Now the next one is that we can, from this stage, we can also go to this stage, not to 1. It means that somebody enters. What's the rate for entrance? Lambda. So this is with rate lambda. And the third one, we would just see that it's no different from the first one. Why? Because in the third one also is the same thing. Somebody from here goes to an arbitrary stage. You can always say that. So we can make a stage, think of a stage there. So it's just the rate of graduation, whatever you want to call it. It's just each of them go there with rate mu. So there are nk minus 1. So it would be nk minus 1 mu. So nk minus 1 mu. So basically you can merge these two states. So forget this one and forget this one. So basically there are only two ways that this Markov chain can evolve. One of them is that somebody goes from intermediate stage to a stage after that, or the last stage to whatever is after, which would be with rate Ni mu, because there are n independent applicants there, which each of them go to the next stage with rate mu. And there's one special kind of state, which is when somebody enters, a new applicant, which happens with rate lambda, independent of the number of people in that system. Is it clear? Yes or no? you can shake your head and tell me. You don't need to talk. Just give me a sign. So, the next question is question number 9. Question number 9 talks about birthday processes. Okay, this is good. This is good. In this way, you can help me, I guess. Yes. So, we have a birthday process with, so since it's a birthday process, 0, oh, it starts at 1, sorry. 1, 2, 3, and okay. And the birth rate is 0, so everybody just dies in this society, basically. Well, oh, sorry. Just to keep the notation backward. It's not really important. It's just that to recognize it even in the first. So this is a simple death process. They just die. Nobody is born. Now, the question is, what's the PIJT? Let's first see what it means. That's the most important thing. So what's the meaning of this PIJT? Exactly. So it's saying that what's the probability that we are now at stage I, we go to stage J after t seconds, t time units, whatever it is. Now, this is a death process with rate mu. I guess it should be independent of the, yes, it is. So it's rate mu. So it's rate mu. So any guess what's the kind of process you're looking at? No, that's the name. There was a better name for it that you know. So what kind of process was a process which, first think of it the other way around, maybe it's even easier. A birth process that goes up by 1 and each time with rate lambda. What was the name of that process? Independent increments and stationary increments with rate lambda and exponential. Yeah, it's called Poisson process. So it's the same thing, but it's the Poisson process is going down, no difference. So it's just the same thing, because in Poisson process you don't talk if you're going up or down. You're just saying that we are here, we go to the next. So Poisson process was a counting process, 1, 2, 3, 4. It just went up always by 1. They were independent stationary increments and all those nice things that we found out that it's exponential in between. So it's also the same thing, but instead of 1, 2, 3, 4, it's just the other way around. Nothing really fancy. There is only one small twist that we will find it, because that one could go up to infinity, this one will stop at 0. You cannot die negatively. So first assume that J, well, obviously, so there are some trivial cases that we handled pretty fast. If I is less than J, this is 0. Done. You cannot go that way. Nobody is born in this society. Now, the case which is easy to handle, in fact, all cases are easy, but let's think of it like this. That I is greater or equal than J, which is strictly greater than 0. Okay, so what's the probability that from here we come here, or here, or here, or here, but not here? Forget this one. So this means that we want I minus J happenings in t times. So when you had a when we had a Poisson process, we said that probability of going from state I to state J, number I to number J bigger, was e to the power of minus lambda t to the power of J minus I divided by J minus I factorial. We said that when, oops, sorry, there is a t here. We said that when we have a Poisson process at time t, it's like a Poisson distribution with rate lambda t. That was one of the basic results in the Poisson process. Now exactly the same thing is happening here. Just there is a little bit difference. Our rate is called mu, not lambda. So it would be e to the power of minus mu t, then mu t to the power of I minus j. Why I minus j? Because I is now bigger number, j is a smaller number. So you want, for example, if you are in a state 10 to state 9, you want 1 happening in t seconds. So this would be the rate, mu t. You want only 1 happening. I minus j would be 1. I minus j factorial. Done. So just let's repeat what we did, because it's a very, it should come to you naturally. You do not need to think about it. It's just saying that a pure depth process with a rate, a fixed rate, is just like a Poisson process, which is instead of going up, it's going down. So we want it go from stage I to stage j in t seconds, t time units. So we know that it's like a Poisson process. A Poisson process for t time unit has a rate t lambda, in this case t mu, and we want j minus I happenings. That's all. Now this would be good for this case, up to 1. But there is a small problem for coming to j, to 0. Any guess what's the problem? So we are using this is not exactly a Poisson distribution, a Poisson process. Because if it was a Poisson process, we had minus 1, minus 2, minus 3, all these things. Okay? So probability that after t seconds, we end up here is equal to the probability that after t seconds, the original Poisson process ended up here or here or here or here or here. So if you are at state 10, let's say, and you look at a Poisson process, and this Poisson process has 11, 12, 13, 14, any number happenings, all of them you would end up here. So that's the only difference between the Poisson process and our depth process. So we just have to add all those probabilities. So probability of going from I to stage 0 in t seconds would be a summation over all, if we want, if I minus, let's just write it down, it would be easier to write it down. It will be k from I to infinity. It means that either I death happens, or I plus 1 death, or I plus 2, because when we hit 0, we would stay at 0 up to infinity, but our original Poisson process would continue generating numbers. So any of these things would be mu t, I minus k, I minus k factorial. So k minus I. Done. Now let me see if I have it correctly. Yes, that's it. Oh, oops, sorry. There is no minus I. I didn't need to do that anymore. Because I just want k happenings. It would be either I happening or infinite happening. I've already known the number of happenings. Mu t to the k. Sorry. Mu t to the k, q factorial, yeah. Because what does this mean? Assume for time I, for k equals I, it means that e to the power of lambda t, mu t to the power of I factorial. It means I happening in t seconds. So if you start at stage I, if in t seconds I Poisson happenings happen, you end up in 0. I death. But if I plus 1 death happens, so you still end up in 0. If I plus 2 happens, everything above I would give you 0. So that's why you have to add all those things. So basically you can think of it as a kind of truncated process. So it acts Poisson. Here, at this point, everything would be just added up to 0. Is it clear what's happening here? Yes?
The answer for PIJT is?
So there are two cases. There are different cases. So this would be the case that, so this case is this one. When I is greater than or equal to j and greater than 0 strictly, when I is greater than equal to j, which is equal to 0, it would be this case. And when I is less than j, Pij t would be 0, because you cannot go backwards. So there would be all these three cases that you have to write down. Yeah, some of them are trivial, but remember not to forget these trivial cases too, because there is no restriction on ing. So can you just think of a way to estimate this number? You cannot add up to infinity. Not even estimate, to calculate it directly. Something add to 1 normally, then there's nothing about probability. So this thing plus something equals to 1. What's that something? So 1 minus the probabilities of going up to here would be, so this would be equal to 1 minus sigma Pij t, j equals I to 1. It's a backward summation. So it's like saying that we want, what's the probability that in t seconds we go from I to 0? It's 1 minus probability that we go from I to I, or I to I minus 1, up to I to 1. The rest of them is for that. That's another way to write it down. Or if you want to make it nicely, you can just, well, this summation is going backward, remember, it's I to 1. You can write it from 1 to I, if you like. Both are correct. In fact, it's better to write it from 1 to I, lower bound to upper bound. Now, so the idea behind this example, I think it's a really nice example, is just to show that how to relate these processes to each other. Now, any questions? The next question is number 13. Number 13. Okay, this is a... So this now is a little bit less abstract. Yeah, it has some numbers. Talks about a barber shop which has a single barber and a room for 2 customers. So we have a barber which people come and go out, and they come with rate 3 per, it's lambda equals 3 per hour. And the service terms are independent exponential and with mean. So is 1 over 4 hours. So just note that one of them is a rate, one of them is a mean. So that's a very big deal, of course. Now let's see what we have here. What's the average number of customers in the shop? So first, we just write down the birth date process. So how many stages do we have? How many? 2. So our stages is the number of customers in the system. There's only a 0 or 1 or 2. So we go from 0 to 1 with rate 3. It's the rate that customers come. From 1 to 2, again, we go with rate 3. We don't go up because whoever comes and sees 2 people are there, he leaves. Now, from 2 to 1, we come back with rate, what? 4. Yeah, so just remember to inverse this, because that was the mean. So maybe it was better if I wrote it like this, but it's just the same thing. Just remember, this is, if you look at the units, this is hour, this is 1 over hour. So if you just make sure you don't make the mistake in units. So 3, 3, 4, 4. So this would be our Markov chain, birth date process. Then we have to solve it and find the average number of customers in the shop. So how do you solve and find the probabilities? Where do you get the equations, those nice equations to solve this, find the stationary probabilities? Huh? Any idea? Yes?
Poisson process?
Yeah, but this is even easier than those things because you started looking at the cuts here and here, and then said that the rate that go here equals the rate that comes back here, and then solve it. It's in your book on page, if you have the book, it's on page, let me find it. On page 370. If you want to. So we look at so there are different ways to look at it. You can either look at the nodes and say that the rate that they enter node 1 equals the rate that they exit node 1 because it's just rate in equals rate out. It doesn't explode. Otherwise it would explode if the rates are not equal. Or you can look at these cuts. Say that, so the number of people that go this way equals to the number of people that go this way. But don't look at the cuts for the time being, just look at the nodes because this is a special case that you can look at the cuts. Now, so for the first one, we come here with rate. So let's make it a little bit abstract. So we have rate lambda 0, lambda 1, mu 2, mu 1. These are the names. Okay, and this is P0, P1, P2. Okay? So let me just make sure if I don't make a mistake. So going out here would be with rate lambda 0. So with probability P0 you're here, with rate lambda 0 then you leave here. This equals to the rate that you come back here. It's mu1, P1. Then you also have the same thing for here. So the rate in here is lambda 0, P0 plus this rate which comes here, which is P2, mu2, equals the rate which goes out of here, which is P1, lambda 1 plus P2, mu1. And the last equation would be for this line, which would be P1 lambda 1 equals P2 lambda mu2. So these three equations, we have three equations and three what do you call it? Three unknowns. We solve it and we find P0, P1, and P2. Let's do it then. So my rates would be I just have my solution here, so I guess I have to write it down and solve it. So let's see. We have 3P0 equals 4P1. We have 3P0 plus 4P2 equals P1, 3 plus 4. And we have 3P1 equals 4P2. Okay? Yes?
Now the second equation is that P1 lambda 1 plus P1 mu1.
This one?
Yeah. On the right.
P1 lambda 1 plus P1 mu1. Yes, thank you. So it was this rate which goes out of here plus this rate which goes out of here. Okay? So then we have these three equations and three unknowns. You have to solve it. The solution would be, since I have the solution here, I wouldn't solve it, but it's going to be, you know how to solve it. Okay. Yes? It's 16 over 37. P1 would be 12 over 37. And P2 would be 9 over 37. Okay? So these would be the probabilities that you would be in these states. Now the question is asking you what's the average number of people that are in this system. So remember, one of the interpretation of probability was the long run average. So 16 over 37 percentage of the times you will be in this state, 12 over 37 percentage you will be in this state, 9 over 37 state you will be in this state. So what's the average number? You have to multiply it by the number that are in each stage and add them up. So the average number of people would equal to, well, this thing multiplied by 0, which gives us 0, 12 over 37 multiplied by 1, plus 9 over 37 multiplied by 2, which gives us 30 over 37. So that's the average number of people in the system, which is less than 1. It need not be less than 1. It can be more than 1, so it just depends on how you work. So you can guess that if, for example, we raise this mu, we might go up, which is the question for the part 2, I guess. So part 2 talks about, part 2, sorry, that's part 3. Part 2 says the proportion of potential customers that enter the shop. How do you find that? Guess. The proportion of them that we are not in a state 2. That's right. But think of it as a better, there is a better way to even think of it. So the proportion of them that we are not in a state 2 would be this plus this, okay? Which is right. So it would be 28 over 37. But assume that it's a huge number. There's a lot of numbers that you want to add up. So how do you think, and it's hard to add it, then how do you think of it? So 1 minus that one. And forget the probability argument. Who are the people that don't enter? They are the people who come to your system and see that there are 2 people there. So 9 over 37 of the entries see this thing. So they come and say, oh, there are 2, they leave. So 1 minus that would be the people who don't see that. That's how you can interpret it even easier than that. Because then you don't have to add up all these messy numbers. Or in fact, you can, if you want to find that number to solve this equation, you just find this one and then you even don't go and find the other ones. 1 minus that would be the solution. So we look at P2, we say that 9 over 37 of our entrances see 2 people in the system and they leave. So 1 minus that is the number of people that don't see 2 people and thus come in. So 1 minus 9 over 37, this is part B, which would be 28 over 37%, which is roughly, how much? 75%, nearly. So 75% of our customers come in. The rest don't come in. Now, the second question says, the second part of the question, if the barber could work twice as fast, how much more business would he do? Now, first the question, if our barber works much, much faster, do you think that the average number of people in the system will go up or down? If it works at rate infinity, what's the average number of people in the system? Nearly 0. Whoever comes just gets the service and leaves. So you can think that, you can have this sense that, okay, the average number of people in the system would go down when he works faster. And let's see, and the proportion of people that enter, would it go up or down if our barber works fast? Down. So if he works fast, everybody who comes just in, we even never get to state 2, so everybody enters. So you can guess that the proportion of people that get served also goes up. Now, if the answer that you get is different from that, there's either something wrong with our intuition or there's something wrong with our answer. I'm not telling that rely on your intuition a lot, but when you develop a good sense of intuition for these things, you can easily guess how would be the direction of the change in the solution. Okay, let's see, how much faster does he work? So twice faster means that mu, instead of 4 hours, it would be, this is the rate, so the rate would be twice faster. So all these equations would rate the, so let me just write it here. So rate mu equals 4. So the new rate, which we call it mu star, equals 8. Okay? So you just, instead of these mu's, you put 8. So this would be 8. This would be 8. This would be 8. I'm being lazy. This would be 8. And the new solutions would be, let me write them here. It's messy there. So P star of 0 would be 64 over 97. P star of 1 would be 24 over 97. And P star of 2 would be 9 over 97. So these would be the new probabilities. And how I derived it, I just solved the same set of equations for these new numbers. Nothing really fancy. But please, at least once solve those equations. It's not hard, it's nothing, but do it at least once, because during the exam you have to do it. And you'd better do it for the first time, not during the exam, but before that. It's just nothing, it's just a normal set of equations. And the loss proportion in this case would be, we have, in the previous case, we lost 9 over 37 of the customers. That was the number of customers that didn't come in. In this case, 9 over 97 is the number of the customers that don't come in. So if we look at the ratio of the people who come in, it would be, do I have it correct here? Yes. So in this case, it would be 88 divided by 97 is the percentage of people served, which is roughly 90%. So in this case, we serve 90% of our customers. In this case, we serve 75% of our customers. So our barber working twice faster can give you 15% more revenue, you can say, or more customers served, whatever you want to measure, however you want to measure it. Now you can make your question different. It's not in this, but you can just assume that you have 2 barbers, and both of them work at rate 4. So what does it mean? It means that when you're in stage 1, you come back here with at rate 4 because it's just 1 barber working at 4. But you have 2 when they come back here. There are 2. It's minimum of 2. What do you call it? Minimum of 2 exponential. So the rate would be 8. The rate would be added. So this would be the case something in between, because you come from here to here at rate 8, but again from here to here at rate 4. When our barber worked twice faster, both of these were 8. So this is another case. You can analyze it, and you can guess that the number would be something between these 2 numbers. Nothing fancy. Now, the last question that I'm going to solve is question number, let me see which one I'd rather solve. So I'd rather solve number 11. That's nicer than number 16. Because number 6, let me just make sure which one is. I think number 16 is, yeah, let's do number 11. Okay, is this? Okay, number 11. Can I erase this? Okay. So, number 11 talks about a Yule process. That's something which always is born, never die. Now, suppose that x0 equals 1. So you start at 1. Oh, wait, what am I writing? Forget this. Let Ti denote the time that it takes the process to go from a population of size I to size I plus 1. So it's a process like this, which only goes up I plus 1. Okay. Now, Ti is the time, so T1 is the time that it takes going from here to here. T2 is this. Ti is this, the time that you go. First, argue that these are independent exponential with a rate, lambda I. So basically each, a Ieorertsj process is the process that at this stage there are three individuals which each of them give birth to a new individual at rate lambda. So at stage I, the rate of going up would be I lambda. Is it clear? I independent individual, each of them giving birth at rate lambda, so the total rate of going from here to here would be I lambda. Now, the first thing is saying that, argue that the time that it takes from here to here is independent of the number that it takes from here to here, which is, I think, obvious. There are two independent random variables. It's just, this is e to the power of, this is an exponential with rate I lambda, this is an exponential with rate I minus 1 lambda, and they're independent. Just as, remember, it's not talking about cumulative time from here to here. It's just saying that the time from here to here is independent of the time from here to here, which is nothing. I think this should be clear. Now, the next step says, let x1 to xj denote the independent exponential random variables, each having rate lambda. So we have, now, it's a totally different setting. So we have x1 to xj, which are IID, and they are exponential with rate lambda. Now, it says, and interpret each of these as a lifetime of a component. So x1 is lifetime of component 1, xj is the lifetime of component j. Just interpret that. Argue that maximum of x1 to xj equals epsilon 1 from epsilon 2 to epsilon j when epsilon I are independent and they are exponential with rate lambda I. Oh, no. They are exponential with rate, so let me write the rates because I need it. So epsilon 1 to epsilon j. So this one would have j lambda. Then epsilon 2 would have j minus 1 lambda, if I'm not mistaken. Yeah. So the rate for this one is this, the rate for this one is this, and the rate for the last one would be lambda. Okay? So now he's saying that we have some IID random variables with rate lambda. The maximum of them is equal like summing up some independent epsilons which add up like that. Now, any idea why? Because if I explain it, it will be very clear. So just take some guesses for that. The hint is, well, even the hint is not as much important as the first thing that it said. Assume that these are lifetimes, x1 to xj. So what's the maximum of lifetime? Maximum of lifetime is the time that the last one fails. Okay? So we start at state 1. Let's say we start at state, well, that's 1, it's fine. State 1 is the state that nobody has failed yet. Then we go to the state that 1 has failed. Then we go to the state that 2 has failed. And then we go to at the last one, we go to the state that j has failed. Okay? So this maximum is just sum of these numbers of these failures, these times of failures. Okay? But what's epsilon 1? Epsilon 1 is lambda j. Each of them fail with rate lambda. So the whole thing fails at rate lambda j. So the time for the first failure is exponential with rate lambda j. Because one of them fails, then you go to the next step. The time for the second failure is j minus 1 lambda, because now you have j minus 1 items, and each of them fail with rate lambda. So when you add, this would be the time until the first one fails. This would be the time until the second one. Time between the first and second failure, time between the third and fourth failure, up to n. So if you add them up, you would get the time from 0 to the time that the last one fails. So that's the whole rationale behind it. It's saying that maximum of these failures equals to just time till the first one fails, the second one fails, till the last one fails. And why could we make this argument? Because these are exponential and these are all independent. They are memoryless, all these nice things that we had from birth-death process. So basically I said that this looks like a birth-death process which there is no death, it's only birth. Okay? So just to go fast over it and then go to the next step, it says that maximum of subatomic components is just like lifetime, so it's adding the lifetime till the time that the first one fails, then add it to the difference until to the second one fails, then the third one fails, and so on. So you just have to, if this is xj, let's say call it xk, this is the maximum, so the others have failed in between, so you add these times and you get the time that the last one fails. The distribution of this one is this, the distribution of this one is this, the distribution of this one is this. So when you add these epsilons, you are just adding everything and you're getting the maximum time until the last one fails. Now, part C, in fact we solved it now. Part C is now really straightforward. It says that show that probability that T1 plus Tj is less than T equals to something. So T1 until Tj, what's it? It's the time, this T1 is this one, T2 is this one, Tj is the last one. So this is the, so basically it's saying that show that until time t, what's the probability that at time t all of them have failed? It's like saying that what's the probability that the maximum lifetime is less than t?
So T1 is equal to epsilon?
Yeah, T1 would be epsilon 1. Time until the first one fails. So basically this is saying, it's telling you what's the probability that all of them fail before time t, which equals to the probability that the maximum is lifetime is less than t. Just saying it it's just saying something in two different ways. The probability that all of them fail before t equals to the probability that the maximum lifetime is less than t. So this would be equal to probability that maximum of xj's is less than t. But each of xj is a exponential variable which is independent. They are also independent of each other. So it's just multiple of each of them to be less than t. So if something is distributed as an exponential, 1 minus e to the power of minus lambda t would be the probability that it would fail until time t to the power of j. Let me just make sure. Yeah. So let me just recap it. So we said that what's the probability that t1 plus tj less than t? This means that all of them fail before time t. It means that the maximum of all the lifetimes is less than t. Each of the lifetimes is a exponential random variable. So we say 1 minus e to the power of lambda t is the CCDF. Is the CDF is the probability mass less than t. Since they are all independent, you just multiply them by each other. So this would be the probability that all of them fail before time t, which is equal to the probability that the maximum lifetime equals t. And the last part says, use part C to obtain that P1JT. Okay, now this should be trivial now. Now let's go back to the setting that we had in the beginning, that Ieorertsj process, which was from 1 to I plus 1. So it says that what's the probability of 1 j t? It means that at time t we have gone from 1 to j. Okay? Any idea? Do you have the book? So look at what it tells you. It tells you 1 minus e to the power of minus lambda tj minus 1 minus that. So basically what it's telling you is this. This is equal to probability that t1 plus tj minus 1 is less than equal to t minus probability that t1 plus tj is less than equal to t. This is just, what does this mean? This means that this is the probability that the maximum of j minus 1 is less than t. It means that all the first j minus 1s fail, minus the probability that all j fail. So this would remain for us only the event that j minus 1 of them failed until time t, but the last one didn't fail at time t. So basically this is saying this probability is the case that from 1 to j minus 1 at least fail at that time. It might be as well that jh1 has also failed. So this probability gives us what's the probability that from I to j minus 1 fail before time t. Now this has two cases. In some of these cases, the jh1 hasn't failed until time t. In some cases, the jh1 has also failed before time t. So this one is the probability that all of them have failed time t. So then when deduct this from this, it just would remain us for one case, which is 1 to j minus 1 have failed till time t, but the last one hasn't failed yet. Is it clear or no? Because this can be a little bit tricky. Yes? No?
Can you repeat?
Okay, yes, why not? Let me just rephrase it in a better way. Maybe it's Okay, so look at the interpretation that we had here. So this would be equal to probability that maximum of xj, j between, well, let's call it k. K between 1 and j minus 1 is less than equal to t minus the probability that maximum of xk, but this time k is between 1 to j is less than t. This is just the same interpretation as we had there. So basically it's saying what's the probability that when we have j minus 1 they all fail before time t? So this would have two cases. Assume that we have j items. If all of them fail before time t, this event has happened. Because when all of them have failed time t, then j minus 1 of them has also failed. But there's also this case that only the j minus 1 of them have failed and the last one has not failed yet. Still this event has happened. So this event has two cases. The case that all of them have failed time t, or only j minus 1 of them have failed till time t. But now, the second one says, what's the probability that all of them have failed till time t? So the deduction of this event from this event will remain only one event for us, that j minus 1 of them have failed till time t, but the last one have not failed yet. So we will go from state 1 to state j in t seconds. That's what we are saying. That we had 1, now we only have j. We don't have more than that, and we don't have less than that. That's all. Because if we only think of this part, we might have 1 to j plus 1 to j plus 3. We are adding everything to each other. It's like saying that, let's think of it in numbers. Maybe that's more clear. Assume that you are talking about 10 seconds, and you have 5 items. So the event that at least 4 of them have failed till time 10, it means that either 4 or 5 have failed till time 10. But the event that all 5 have, so this is one event. So event 1, at least 4 have failed. Then we talk of event 2, that at least 5 have failed. Now, if we deduct the probability of this one from this one, it would give us the case that exactly 4 have failed. Is it clear now? So this is also the same thing. So we are saying that what's the probability that j minus 1, at least j minus 1 have failed? What's the probability that at least j have failed? You deduct them. What's the probability that exactly j minus 1 have failed? This would be part D of this equation. It is this what you call it? This question. And the last part is really just trivial. It tells you now, we talked about 1 to j. It means that starting from the first one going to j. Now it says that argue that going from I to j, what would that one give to you? If you look at that distribution, it really looks like so look at part D. So after simplifying this thing, it would give us e to the power of minus lambda t, 1 minus e to the power of lambda t, j minus 1. So the distribution of p1jt equals to this, which is a geometric distribution. Okay. Now the second case says what's the probability of pijt starting at I? Starting at I is like starting at I independent q's and just continuing them, which would be so adding I one of these random variables to each other. But before in page, I have it here, on page 88, question number 23, you showed that when you have some geometric random variables and you add them up, it would be something called negative binomial, which that's the distribution of it. So this step is not at all intuitive, I totally agree, but you have done the math all before in one of the questions, so we don't go through the math again. But the only argument that you need to make is this. So what we have is, if we start with 1 person, we get to j person in t time with this probability. Now, if we start with I person, what's the probability that we get to j in t time? Well, starting at I person, it's as if we just have I different processes that start at 1. Because each of them independently give birth to the person after that. So there is no difference by looking at all of them in one thing or just looking at I independent things. Because they're exactly the same thing. It's like each of them would have a family tree which goes down independent of the other ones. So pijt would be just, that random variable would be just summation of I of these random variables. But we know that when you have geometric random variables and you add them, you get negative binomial random variables, which this distribution is given here. Question number 23, page 88. That's, I think, in one of your previous homeworks. So that's one of the cases that you can use the previous results, which don't look intuitive at all. I think this should give you a feel about how the Markov chains work. Normally, it's easy to work with Markov chains. This memory-less property makes your life easy. Any questions? Okay. I promise next time your own TA would be here. He would be much better than me. Yes. Oh no, it was just deleted. It was something that I had deleted. Yes,